Space and time. We live every moment immersed in them. But what are they really? At first glance, nothing seems more obvious. Space is the vast expanse that contains everything, and time is the flow of events from past to future. We check clocks and calendars, measure distances with rulers or GPS, and it all feels like the basic, unchanging backdrop of the universe. Yet over the last century, physicists have discovered that these concepts are far stranger and more profound than anyone imagined. Space and time can bend, stretch, and even fuse together. They are not merely a passive stage on which the cosmic drama unfolds. They are dynamic actors in that drama. Understanding what this continuum actually is has become one of the greatest scientific adventures in history. We'll start with the common-sense, classical view that stood for centuries, where the two were absolute and separate. Then we'll delve into Einstein's revolutionary ideas that merged them into a single fabric called spacetime, where distances and durations are not fixed but relative. We'll see how gravity emerges as the bending of this fabric, and how extreme cosmic events like black holes and the Big Bang reveal the continuum at its most mind-bending limits. We'll also peek into the puzzling world of quantum physics, where the arena of reality can behave like frothy foam at unimaginably small scales, or even fade as a meaningful concept. Along the way, we'll consider why time seems to flow in one direction, and ask whether past and future might exist in some sense just as the present does. By the end, we'll circle back to the big question: what fundamentally are these foundations of reality? Are they physical things? Are they just useful ideas? Could they be an emergent illusion from something deeper? These are questions scientists are still trying to answer. What we have learned so far has completely changed our picture of reality. So, let's begin at the beginning, with the intuitive notions humanity held for ages, and see why they had to be turned upside down.
For most of human history, space and time were assumed to be straightforward and independent. Space was thought of as an endless three-dimensional container in which all matter exists. Time was a separate, one-dimensional river that flows uniformly, carrying all events from the past towards the future. This view was codified in the physics of Isaac Newton in the late 17th century. Newton imagined space and time as an invisible stage or grid on which the laws of motion played out. In his words, Newton described absolute, true, and mathematical time as flowing evenly without relation to anything external, and absolute space as existing always immovable and unchanging. In simpler terms, Newton's universe had a single universal clock ticking everywhere at the same rate, and a rigid coordinate grid stretching out infinitely in all directions. If two events happened at the same time for one observer, they happened at the same time for everyone. If two measuring sticks were the same length for one person, they were the same length for anyone, anywhere. Space and time were fixed, objective backdrops. This intuitive picture works extremely well in everyday life. If I'm sitting in a room, I can measure the room's dimensions with a tape measure. Those spatial distances exist independent of me. If I synchronize my watch with yours and wait an hour, both of us will agree that 1 hour passed. We take for granted that there's a common time we all share and a single notion of distance we can all agree on. Indeed, classical physics built on Newton's foundations treated space and time as absolute. Galileo Galilei had introduced the idea of relativity in motion, meaning the laws of physics are the same if you're moving at constant speed or standing still. But even in Galileo's relativity, time itself was universal. Whether a ship was at rest in port or sailing at steady speed, Galileo assumed a second of time was the same for everyone, and space was just the stage in which the ship moved.
For centuries, this view reigned supreme. It's hard to blame people for thinking of space and time this way. After all, in our normal experience, we don't notice anything odd about how time passes or how distances behave. Euclidean geometry seemed perfectly adequate to describe space. Parallel lines never meet, the shortest path between 2 points is a straight line, and so on. And time was like a metronome for the universe, ticking uniformly. Engineers and navigators learned to use these concepts to build structures, sail the oceans, and eventually synchronize clocks across towns and continents. By the 19th century, the ability to measure time and space had become very precise, thanks to inventions like accurate mechanical clocks and careful surveying techniques. And yet, all of this was still built on the comfortable idea that space and time were completely separate aspects of reality, one dealing with where events happen, the other with when events happen. However, cracks in this simple picture began to appear as scientists probed deeper into the laws of nature. One key clue came from the study of light and electromagnetism in the 1800s. James Clerk Maxwell discovered that light is an electromagnetic wave, a ripple in electric and magnetic fields, and his equations showed that these waves should travel at a specific speed, about 300,000 kilometers per second, in a vacuum. This was puzzling. Speed according to whom? Normally, if you measure the speed of a moving object, you have to measure it relative to something, usually relative to yourself or the ground. So, if light has a fixed speed, what is that speed measured against? Many physicists assumed there must be an invisible medium filling space, which they called luminiferous ether, through which light waves propagated. They imagined the ether was an absolute reference frame, essentially space itself as a substance. If you moved through this ether, the speed of light should appear different, like how running into the wind versus with the wind changes the apparent speed of a breeze. In 1887, Michelson and Edward Morley performed a famous experiment to detect this ether wind as Earth moved through space. To everyone's surprise, they found nothing. No change in the speed of light due to Earth's motion. Light always seemed to move at the same speed regardless of how the experiment was oriented or when it was done. This result was deeply mysterious in the classical framework. If space and time are absolute, how could the speed of something be fixed universally? Either the Earth was always magically still with respect to the ether, very unlikely, or something was wrong with our understanding of space, time, and motion. It was Albert Einstein in 1905 who boldly suggested a solution. There is no ether and no absolute reference frame. Instead, the surprising constancy of the speed of light means that time and space themselves are not absolute. To accommodate a universal speed of light, our measures of time and space must adjust depending on the motion of the observer. This was the birth of Einstein's special theory of relativity, and it would forever change how we think of space and time.
Imagine a scenario to illustrate Einstein's idea. You and a friend want to measure the speed of a light beam. You stand still on a platform, while your friend rushes in a fast train in the same direction as the light beam. Intuition from classical thinking might say that your friend, moving along with the light, would measure the light beam's speed as much slower, since she's chasing it, than you would while standing still. After all, if you run alongside a car, the car's speed relative to you drops. But light doesn't behave like that. According to Einstein's theory, and confirmed by experiments countless times since, both you and your friend will measure the speed of that light beam to be 300,000 kilometers per second. The only way this can happen is if some other strange adjustments occur. Time and space themselves must distort to reconcile the measurements. In fact, this does happen When your friend is moving relative to you, time dilation, your friend's clocks, including her heartbeat, aging, any process marking time, will appear to you to run slower than your own clocks. In other words, a moving clock ticks more slowly than a stationary clock, according to an outside observer. Length contraction. Distances along the direction of motion, like the length of the train or the spacing between two milestones along the tracks, will appear shorter from your perspective than they are for your friend. To your friend on the moving train, everything seems normal inside the train, but you observe her train as shrunk a bit in length. Relativity of simultaneity. Perhaps strangest to all, two events that seem simultaneous to you will not be simultaneous to your friend on the train. For example, if two lightning bolts strike the ground at the same moment according to you, your friend might see one flash before the other simply because she's moving relative to where they struck. There is no single universal now that everyone agrees on once we're in relative motion. Each observer has their own slice of time. These effects are not just thought experiments. They have been measured. Time dilation, for instance, has been confirmed by flying atomic clocks on airplanes. Moving clocks really do tick a tiny bit slower compared to ones on the ground. Subatomic particles called muons, produced high in the atmosphere, normally decay in a split second. Yet many more of them reach the ground than expected because from our viewpoint, their internal clock is slowed by their high speed. Length contraction is trickier to directly observe, but it's a logical counterpart to time dilation, and it shows up in particle accelerator experiments where fast-moving particles experience contracted electric fields. The relativity of simultaneity was directly demonstrated in a laboratory in 2011 with precise timing of atomic clocks in motion. Relativity is real. Nature behaves this way even if it defies everyday intuition. Einstein's radical postulate can be summed up simply. The laws of physics, including the speed of light, are the same for all observers in uniform motion. To uphold this truth, space and time have to bend a little. They trade off with each other. A bit of what one observer calls space can mix into what another observer calls time. This sounds very abstract, but think of it like a rotation of axes on a graph. If you have an XY graph and you rotate your perspective, what you call x-axis and y-axis mix together. Similarly, in special relativity, different observers have coordinate axes tilted in space and time relative to each other. What one calls a purely spatial separation might be a mix of space and time for another. This insight led to the famous merging of space and time into a single concept, space-time. In 1908, mathematician Hermann Minkowski, who had been one of Einstein's professors, asserted, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only the union of the two will preserve an independent reality." What Minkowski meant is that events in the universe are best described not by where and when separately, but by a four-dimensional combination of coordinates, 3D for space and 1D for time. We call a specific location at a specific moment an event in space-time. Everyone will agree on an event, say, the event of you snapping your fingers in your room at 3 p.m. local time, but they might not agree on the exact time or spatial distances between events compared to another frame of reference. However, they will agree on a certain unified measure called space-time interval between events, which remains invariant. In essence, space and time individually can stretch or shrink depending on your motion, but the combined distance in space-time stays the same for all observers. This unity of space-time is why we now often think of the universe as a four-dimensional fabric where the 3 dimensions of space and one of time are interwoven. It's important to note that this new picture doesn't make our everyday experiences wrong. Rather, it extends them. We normally don't notice these relativistic effects because at the speeds we move, walking, driving, even flying, time dilation and length contraction are infinitesimal. Only when approaching a significant fraction of the speed of light or in intense gravitational fields, which we'll get to, do these effects become dramatic. Our intuitions have been honed in a regime where space and time appear absolute, but Einstein showed that this was just a special case. Nature's true rules are more flexible. One way to visualize a simple aspect of spacetime is the famous light clock thought experiment. Imagine a clock made of two mirrors facing each other, bouncing a light pulse between them. Each bounce can count as a tick. If this clock is at rest relative to you, you see the light going up and down between mirrors. But if the clock moves sideways relative to you, the light's path slants and becomes longer, like a zigzag. Since light speed is constant, a longer path means the ticks take longer, so you see the moving clock tick slower. That's time dilation in action, derived from the geometry of spacetime. This simple visual reinforces that movement through space affects the passage of time.
Special relativity opened up an astounding possibility. If different observers have their own measures of time, could one observer's future be another's past? Could we travel into the future or past by clever journeys? Time travel into the future is actually permitted and, in fact, unavoidable in relativity. You just need to move very fast or experience strong gravity. A frequently cited example is the twin paradox. Imagine identical twins, Alice and Bob. Alice boards a spaceship and rockets off at near light speed to a distant star, then turns around and comes back, while Bob stays on Earth. Because of time dilation, from Bob's perspective, Alice's clocks ran slow during her voyage, so when she returns, she has aged less than Bob. Perhaps she went out for what she felt was 5 years and came back to find, say, 10 years have passed on Earth. This is not just a theoretical idea, it's a consequence of relativity. In fact, something like this has been measured with less dramatic numbers. Cosmonaut Sergei Avdeyev, who spent 747 days on the Mir space station in the 1990s, experienced time dilation that made him about 0.02 seconds younger than if he had stayed on Earth. He literally traveled a few hundredths of a second into his own future relative to us. Travel into the past, however, is a much thornier issue. Special relativity on its own doesn't allow you to go back in time. You'd have to exceed the speed of light, which the theory forbids. The reason is that as you approach light speed, time slows down relative to others. At light speed, time would stop, and beyond light speed, math would yield imaginary values for time, nonsensical in physical terms. That being said, in the context of general relativity, coming next, there are some speculative scenarios involving things like wormholes or rotating universes that mathematically could allow backward time travel. But these are highly conjectural, likely not physically realistic, and none have ever been observed. So for now, as far as we know, the past is off limits. Nonetheless, the relativity of time forces us to give up the idea of a universal, flowing present moment across the universe. In a sense, every observer carries their own clock and ruler with them, and what one calls now can be another's later or earlier for events far away. That alone is a profound shift in how we view time. It's worth noting that these relativistic effects aren't just abstract or reserved for thought experiments. They have practical consequences. A great example is the Global Positioning System, GPS, that we use for navigation. GPS satellites orbiting Earth carry precise atomic clocks. Because these satellites are moving relative to us on the ground, special relativity says their clocks should tick a bit slower from our perspective. However, there's another effect. Being high above Earth's surface, they feel slightly weaker gravity than we do on the ground. And general relativity, as we'll see, says clocks in stronger gravity tick slower, meaning the satellite's clocks actually tick faster from our perspective due to less gravity. The net result is that without correction, the satellite clocks would drift about 38 microseconds faster per day than ground clocks. That might not sound like much, but even a few microseconds discrepancy can translate to kilometers of error in positioning. Engineers have to program relativistic corrections into the GPS system to get the accuracy we rely on. In short,
our modern technology is subtly but critically dependent on acknowledging that space and time don't behave in the absolute way Newton imagined. Special relativity dealt with observers moving at constant speeds, no acceleration, and with gravity absent. It painted space-time as a unified but flat stage, meaning it's not curved or warped, just a 4D version of a flat grid. Einstein's next question was, how to bring gravity into this picture? It took him another 10 years after 1905 to figure it out, resulting in the general theory of relativity in 1915. The answer was revolutionary. Gravity is not a force that masses exert across space, as Newton thought. Instead, gravity is the result of curvature in space-time itself. Mass and energy tell space-time how to curve, and that curved space-time tells objects how to move. This idea is often illustrated with the rubber sheet analogy. Imagine a stretched, flexible sheet like a trampoline, representing space-time. If the sheet is empty, a small marble placed on it will sit still, analogous to an object moving in a straight line at constant speed or staying still when no forces act. Now put a heavy bowling ball on the sheet, it creates a dip or well. If you now roll a marble near the bowling ball, the marble no longer travels in a straight line. It spirals around the bowling ball, perhaps even orbiting it, much like a planet orbits a star. From the marble's point of view, it was just going straight, but the space it moved through was curved by the presence of the heavy ball. In the real world, that sheet is the fabric of space-time, and the role of the heavy ball is played by massive objects like the Sun or Earth. In Einstein's famous words, matter tells space how to curve, space tells matter how to move. Gravity, in this view, isn't a pull through space, but a push along the curves of space-time. One important aspect of this is that time is affected by gravity just as space is. Near a massive object, time runs a bit slower relative to a region farther away. This has been measured. For example, clocks on Earth's surface, deep in Earth's gravity well, tick slightly slower than clocks on a high mountain or a satellite orbiting higher up. This is called gravitational time dilation. It's as if time itself is stretched out in stronger gravity. If you were to hover near the edge of a black hole, an extremely dense mass that curves space-time to an extreme, time for you might slow to a crawl relative to the outside universe. In theory, you could watch the far future of the universe unfold in fast forward while only a short time passes for you. Of course, surviving such a journey is another matter. Einstein's general relativity provided a new set of equations to determine how space-time is curved by matter. These equations predicted several phenomena that differed from Newton's gravity, and over the years, each of these predictions has been confirmed. Mercury's orbit. The planet Mercury's orbit precesses, shifts slightly over time, in a way Newton's gravity couldn't fully explain. General relativity accounted for that extra perihelion shift perfectly by considering the curvature of space-time near the Sun. Bending of light, gravitational lensing. Newton's gravity acts on mass, so Newton wouldn't have expected light, which has no rest mass, to bend due to gravity. But Einstein's theory said space-time is curved for everything, including light. During a solar eclipse in 1919, stars appearing near the Sun were observed to be slightly displaced from their usual positions, due to the Sun's gravity bending their light on the way to Earth, exactly the amount Einstein's equations predicted. This made headlines around the world, as it was a stunning confirmation that space around the Sun is warped.
Gravitational waves. Perhaps one of the most dramatic predictions. If space-time is a fabric, then masses moving around, especially violently, like two big masses orbiting each other, should create ripples in that fabric, like shaking jello. These ripples are called gravitational waves. Einstein himself was not entirely sure if they'd ever be detectable, because by the time they reach us, they're incredibly tiny distortions. But a century later, in 2015, the LIGO experiment stunned the world by directly observing gravitational waves from two merging black holes billions of light years away. The signal was a faint chirp in the detector as space itself stretched and squeezed subtly by less than a fraction of a proton's width, yet enough for the ultra-sensitive instruments. Since then, multiple gravitational wave events have been measured, merging neutron stars, black holes, etc. This achievement is not only a triumph of technology, but also literally an observation of space-time itself in motion. It's as if we developed ears to hear the universe's fabric quiver. So, general relativity firmly established that space and time are dynamic. They are not a static stage at all. They can bend, stretch, and oscillate. Massive objects create dimples in space-time, affecting the motion of other objects and the flow of time. And energetic events can send shock waves through space-time. In a sense, space and time in Einstein's theory behave almost like a form of matter. They have properties that can change and evolve. A fascinating consequence of all this is that what we perceive as the force of gravity is actually objects following the nearest thing to a straight line in curved spacetime. In curved geometry, a straight line is called a geodesic. Like the Great Circle route on Earth's curved surface is the shortest path between two cities, even though it looks curved on a flat map. Planets orbiting the Sun are just following geodesics in the curved spacetime the Sun creates. They're going in straight paths in 4D geometry, but in our 3D viewpoint, those paths look like ellipses around the Sun. General relativity also blurs the distinction between space and time further under extreme conditions. In the vicinity of a black hole, for example, the curvature is so strong that inside the black hole's boundary, the event horizon, the roles of space and time can swap in a mathematical sense. Moving forward in time inevitably drags you toward the center, just as surely as normal time pushes us from past to future. It's as if the direction toward the center of the black hole is a future direction. Everything must move that way. This kind of mind-bending scenario shows that in the most extreme realms, our separate mental picture of space versus time becomes inadequate. Einstein's theory of spacetime wasn't just about local effects like orbits and bending light. It applied to the entire universe. In 1917, Einstein applied general relativity to cosmology, the study of the universe as a whole. The equations suggested something surprising. The universe should be dynamic, either expanding or contracting rather than static. Einstein, like most people at the time, assumed the universe was eternal and unchanging on large scales, so he initially added a cosmological constant term to his equations to allow a static universe. But not long after, in the 1920s, observations by Edwin Hubble showed that distant galaxies are flying away from us, and the farther away they are, the faster they recede. The universe is expanding. Space itself is stretching over time. Einstein reportedly called his earlier static universe fix his biggest blunder and embraced the idea that our universe had a beginning and is evolving. In an expanding universe, distant galaxies aren't moving through space away from us so much as space between us and them is expanding, carrying them apart. This is an important distinction. There's no center of expansion. Every region of space sees others moving away. If we run the clock backward, we reach a point roughly 13.8 billion years ago when the distances between galaxies, indeed between everything, were zero, a state of extremely high density and temperature known as the Big Bang. It's often said that the Big Bang was the beginning of time and space. What does that mean? In general relativity, it means if you try to extrapolate all the way back, you get to a boundary beyond which the equations break down. Time itself, as measured within the universe, cannot be extended past that point,
It's like asking for a point on Earth further north than the North Pole. Thus, time as we know it started with the Big Bang. There's no before in the usual sense, because time itself is a part of the universe that came into being. However, it's worth noting that modern cosmology has considered scenarios in which the Big Bang isn't a strict beginning of time, but perhaps a transition from a previous state. For example, a bounce from a preceding contraction, or a collision of brane universes in string theory models, etc. We don't know for sure, but at least from the perspective of our observable universe, time equals zero at the Big Bang is as far back as the concept of time can go. As for space, if the universe is finite in size, which we also don't know for sure, it could be that space is like the surface of an expanding balloon, finite but with no edge. Or the universe might be infinite, even from the start, just getting more spread out. In either case, space is not a static backdrop in cosmology, it's dynamic and can stretch. The expansion of space has some non-intuitive consequences. Because space itself expands, it can carry galaxies apart faster than the speed of light without contradicting relativity. Relativity only forbids objects moving through space faster than light, but space itself can do it at once, since it's not a material object. This means extremely distant galaxies can be receding so fast that their light will never reach us. They're effectively outside our observable universe.
It also means that over time, galaxies will appear to accelerate away and eventually even disappear from view as the expansion carries them beyond the horizon of what we can see. Space expansion also stretches the wavelength of light traveling through it, known as cosmological redshift. A photon from a distant quasar emitted 12 billion years ago has had its wavelength stretched by the expansion, so what might have been an energetic ultraviolet photon when it started out arrives as a lower energy infrared photon today. In effect, the expansion of space drains energy from photons, a phenomenon with no real analog in static space. All these cosmic effects reinforce that space and time are part of the physical fabric of the universe. They have dynamics governed by Einstein's equations. The universe has a history in time, a beginning, and possibly a future end or eternal expansion, and it has an evolving size, shape in space. There even is a concept of the age of the universe, around 13.8 billion years, which is essentially the time coordinate difference between the Big Bang and now for an observer at rest relative to cosmic expansion. That's a kind of global time for our universe, often called cosmic time, defined by the expansion. This works because on large scales, the universe looks uniform. Thus, we can imagine all galaxies started from the Big Bang at the same time, and then the universal clock ticked forward as they flew apart. It's a bit like the universe itself provides a preferred time coordinate via its expansion history, even though relativity says locally different observers have different clocks. In the cosmological sense, we all share the flow of cosmic time, give or take some relativistic differences due to local motion or gravity. Up to now, we've been discussing space and time largely through the lens of Einstein's relativity, which is a classical theory. Classical here means it doesn't take into account quantum physics, the rules that govern the subatomic world of particles and fields. Quantum physics and relativity are the two towering pillars of modern physics, but when we try to put them together, things get tricky. One of the biggest challenges in physics today is to develop a quantum theory of gravity, essentially a theory that can describe the fabric of space-time in quantum terms. We don't yet have a complete theory of this sort. Candidate ideas exist, like string theory or loop quantum gravity, but none is confirmed experimentally. Yet physicists have some intriguing thoughts on what space and time might be like at the quantum level. In quantum physics as currently formulated, space and time often serve as a fixed stage, especially in quantum mechanics and quantum field theory. we usually treat time as a continuously flowing parameter and space as a fixed arena where particles move. This approach works exceedingly well for particles and forces, except gravity. However, if space-time itself is something dynamic and physical, per general relativity, then at extremely small scales or high energies, the smooth picture of space-time should break down due to quantum fluctuations. The scale at which quantum effects of gravity become significant is called the Planck length, about 1.6 times 10 to the minus 35 meters, and Planck time, about 5.4 times 10 to the minus 44 seconds. These scales are so incredibly tiny that directly probing them is far beyond our current technology. They make subatomic particles look enormous. But conceptually, at the Planck scale, we expect the fabric of space-time to be deeply foamy, turbulent, or even fractal in nature, thanks to Heisenberg's uncertainty principle. The term quantum foam, coined by physicist John Wheeler, gives a visceral image of what might be happening at the Planck scale. Picture how a calm, smooth ocean appears from an airplane. It looks like a flat, smooth surface, but if you zoom in to where you can see individual waves and then the frothy bubbles at the crest of a breaking wave, the smooth surface is gone. It's a chaotic, fizzing mess of spray and foam. Similarly, from our macroscopic viewpoint, space-time is smooth and well-behaved. Distances and durations have definite values. Geometry mostly follows simple rules. But on the tiniest scales, space-time might be seething with tiny bubbles, twisting and contorting due to quantum uncertainties. Space might constantly warp into tiny curved pockets and then back out, and time might not flow in a simple, orderly way. These fluctuations would be incredibly fast and tiny, so at larger scales, they average out to the nice, steady space-time we experience. Though we cannot observe quantum foam directly, we'd need a microscope far more powerful than any conceivable. Physicists have tried to find indirect hints. For example, some studies look at the speed of high-energy particles from distant astrophysical events to see if tiny differences accumulate due to traveling through a frothy space-time. So far, no conclusive evidence of such effects has been found, but research continues. It's possible that space-time is smoother than some quantum gravity models predict, or that our measurements aren't yet sensitive enough, or even that our whole approach to quantum space-time needs rethinking. There are a couple of major avenues that theoretical physicists are exploring to understand space-time at the quantum level. Loop quantum gravity. This approach attempts to quantize space-time directly. It suggests that space is made up of extremely small, discrete chunks, or atoms of space, often visualized as a network of finite loops, hence the name loop quantum gravity. According to LQG, areas and volumes would have smallest possible units, a fundamentally granular geometry. Space would be like a woven fabric. Zoom in enough and you see the individual threads or loops. LQG also implies that time might be quantized in some way, or that time is defined through the changes in this discrete space fabric.
String theory, on the other hand, starts by replacing point particles with tiny strings vibrating in perhaps 10 or 11 dimensions. Most of those extra dimensions are presumably curled up at microscopic scales. In string theory, gravity is carried by a particle called the graviton, which is one of the string vibration modes. But more intriguing is the idea coming from string theory's holographic principle and CFT correspondence, the possibility that space and time might be emergent phenomena. Emergent means they aren't fundamental at the deepest level, but arise from something else. In this case, maybe from the entanglement relationships in a lower dimensional quantum system. A famous example is that a 3D space with gravity, like a volume of space, might correspond to a 2D system without gravity on its boundary. In such a scenario, what we experience as space is kind of like a hologram projected from more fundamental degrees of freedom.
Some researchers have found that the more entangled two sets of particles are in a certain quantum model, the closer their corresponding regions are in the emergent space. In principle, if entanglement patterns change, the shape of space could change, leading to a geometric view of quantum physics, where entanglement is like the glue of space. This is highly theoretical and not experimentally confirmed, but it's a fascinating attempt to reconcile quantum mechanics and gravity. Time as an emergent concept. A related line of thought asks if time itself might be emergent. In some approaches to quantum gravity, there isn't a fundamental time variable. The theory might be timeless underneath, and what we call time comes out of relationships between quantum states. This is speculative, but it addresses long-standing puzzles about the nature of time in quantum cosmology. For instance, the Wheeler-DeWitt equation in quantum gravity, which, bafflingly, doesn't contain an explicit time parameter, suggesting that at a fundamental level, time might not exist the way we think. None of these theories are proven, but they highlight that when we ask, what are space and time really, the answer might be that on the smallest scales, they dissolve into something else, whether it's discrete brains or a network of interactions or an emergent tapestry from quantum information. It's analogous to asking, what is water? To the naked eye, it's a continuous fluid, but we know it's actually made of molecules. Space-time might similarly have a substructure. However, it must be emphasized that for now, general relativity and our earlier description of smooth spacetime has passed all experimental tests in the domains we can observe. So our earlier description of smooth spacetime and its bending in gravity is extremely accurate for anything above the submicroscopic scale. The quantum perspective becomes critical only when dealing with singular extremes, like inside black holes, or the very beginning of the universe, where densities reach Planck-scale conditions. The quest to experimentally bridge this gap is ongoing, whether through high-energy physics, astrophysical observations, or perhaps someday building detectors sensitive enough to see quantum fluctuations of space itself. If and when scientists succeed, we might finally get a definitive answer to what space and time are made of. Up to now, we've mostly discussed time as a dimension, similar to space in many respects. Yet there's a glaring difference between space and time in our everyday experience. Time has a direction. Space does not, at least not an obvious one. We remember the past, but not the future. We are born young and grow older, never the reverse. We can move freely in space, forward, back, left, right, up, down, but we seemingly cannot move freely in time. We are swept forward in one direction. This directional quality of time is often called the arrow of time. What causes it? Interestingly, if you look at the fundamental laws of physics, Newton's laws, Maxwell's equations, Einstein's relativity equations, even the basic equations of quantum mechanics, they are largely time-symmetric. This means if you took a video of a fundamental particle interaction and played it backward, it would still make sense according to those laws. So why then do we see irreversible processes all around us? Eggs scrambling but never unscrambling, smoke dispersing but never gathering back into the chimney. The answer comes from a branch of physics called thermodynamics, specifically the second law of thermodynamics. This law introduces the concept of entropy, which is a measure of disorder or randomness. It says that for an isolated system, entropy tends to increase or, at best, stay the same over time. Increasing entropy essentially defines a direction. The future is the direction of higher entropy. Imagine the simple example. A glass falls off a table and shatters on the floor. This process is easy to understand in forward time. An ordered object, low entropy, breaks into a disordered pile of shards, higher entropy. The reverse, the shards reassemble into a glass and jump back onto the table, would be extraordinarily unlikely, so much so that we never see it happen. There's no law of physics preventing the reverse on a microscopic level,
The atoms could, in theory, all collide in just the right ways to form a glass, but it's so absurdly improbable that for practical purposes, it's impossible. Thus, we get an arrow of time. It's the direction in which entropy increases. Life itself, our memories, aging, all these things are tied into this entropy arrow. When we remember something, we're observing traces, like records, brain states, left by a past state that was more ordered. We don't have memory of the future because the future hasn't left any traces yet. It hasn't happened. How does this thermodynamic arrow reconcile with our earlier discussion of space-time as mostly symmetric fabric? It turns out that the arrow of time is not built into space-time at a fundamental level. Instead, it comes from initial conditions of the universe. The universe began in a very low entropy, highly ordered state. Think of the Big Bang. Although it was a hot, uniform plasma, that uniformity and tiny initial smoothness hides a low gravitational entropy. From that highly ordered beginning, entropy could only increase, giving a direction to time. If the universe had started in a high entropy state, we might not perceive an arrow of time. Life and complexity as we know it wouldn't likely exist in such a scenario either.
Now, it's important to note, nothing in relativity forbids an arrow. Relativity doesn't say time must be symmetric, it just doesn't dictate an arrow. The arrow comes from outside relativity, from the world of statistical physics. But once an arrow exists, globally from the Big Bang, it permeates all the processes we experience. In fact, we can incorporate it logically. We label the direction of time from past to future as the direction in which entropy increases. This is how we, beings made of many particles, interface with time. Another aspect of the arrow is psychological or perceptual. Why do we feel time flowing? Physics doesn't fully answer that. It could be an emergent phenomenon from how our brains process information in one direction, again tied to entropy and memory formation. To physics, all of time, past and future, can in some sense be treated as an already laid out dimension, like the frames of a film strip. But to us, only one frame, the present, is illuminated at a time. Some philosophers and physicists argue that the flow of time is more of a subjective impression, and objectively, time is just a coordinate like space. However, our conscious experience definitely treats time differently than space. The arrow of time is a reminder that time, as we experience it, has layers of meaning. There is time as a coordinate in space-time, where past and future are just different locations in 4D, and then there is time as experienced, with a flowing quality and an irreversible aspect. The flowing aspect might not be a fundamental physical thing, but an emergent one from complex systems like us within the universe. It's quite fascinating that our best fundamental description of nature, Einstein's spacetime, doesn't by itself distinguish past versus future. It's kind of an eternal 4D landscape. Yet everything we do in daily life screams that there is a difference. So when we ask, what is time, we have to consider both the geometric concept in physics and the experiential, thermodynamic concept. They are connected, but not identical. The arrow of time, anchored by entropy, gives time a kind of one-way street character that space doesn't have. Our exploration of space and time would be incomplete without touching on some of the philosophical questions that arise. Einstein's relativity, especially the unified spacetime view, has suggested a picture in which the universe might be like a four-dimensional block, often called the block universe concept. In the block universe idea, all events, past, present, future, coexist in a certain four-dimensional structure. We experience them in a sequence, but that might be akin to how we perceive our path through space. Just because we're not now in Paris doesn't mean Paris ceases to exist. Similarly, just because we're not in the year 1800 or 2100 doesn't necessarily mean those times don't exist in some form in the space-time continuum.
This view is closely related to a philosophical stance called eternalism, which holds that past, present, and future are equally real. Eternalism finds some support in relativity, since different observers can slice the space-time loaf at different angles. One observer's past might be another's still in the future due to relativity of simultaneity for distant events. Contrast this with presentism, the common-sense philosophical view that only the present moment is real. The past is gone, the future has not yet come into existence. Presentism has a challenge in relativity because present can be different for different observers when events are far apart. There's also a middle ground theory called the growing block universe, which says the past and present are real, but the future is not yet real. The block is growing as time progresses. These ideas venture beyond testable physics into interpretation, but they show how our scientific understanding of space-time influences broader thinking. Einstein himself, after the death of a friend, wrote a letter consoling the family with a very block universe sentiment. For we convinced physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. He meant that from the perspective of physics, time is just another coordinate, and all moments in time exist in some sense. However, not everyone agrees with that interpretation.
Some argue that space-time is just a mathematical model, and one shouldn't assume that the future already exists. This ties to what we saw in the earlier philosophical piece, the distinction between the map and the territory. Space-time, as used in physics, is like a map of all events, but does the map itself exist as a tangible thing? When we say the event of Julius Caesar's assassination in 44 BC exists in space-time, we mean it has coordinates in the 4D continuum. But isn't that just a way of cataloging? One view, like the SciTech Daily piece hinted, is that only events happening now are actually happening, and space-time is a useful concept to record where, when events occur and how they relate, rather than a literal giant frozen block. This becomes almost a semantic debate. What do we mean by exist? The chair in your room exists. Does tomorrow exist? It's not here yet in any observable sense. Physics can describe it as part of space-time if we treat time as a dimension, but that might be more of a calculation tool. These discussions bleed into metaphysics, and scientists tend to remain grounded by what can be observed or measured. So far, no experiment can reach into the future part of space-time and pull something out. We only have access to the past via records and memory, and to the present moment as it happens. There's also the question of whether space-time is fundamental or if something deeper underlies it, as we discussed with quantum theory. If space and time are emergent, then asking if past and future exist might be like asking if the average temperature of a gas exists. It's a useful concept, emergent from underlying particles, but not something with independent reality of its own. It could be that space-time, including all its events, is a secondary structure arising from something more basic. Quantum events, information, logic, who knows? As a fun perspective, one famous phrase goes, "Time is what keeps everything from happening at once, and space is what keeps everything from happening to you." In other words, space and time separate events so that our reality isn't an overlaid jumble. They provide order, distinct locations, and distinct moments. Whether they are things or concepts might depend on the context. In physics, we treat them as something like a field that has properties, curvature, etc., implying they have a physical essence. In philosophy, one might treat them as part of our mental framework for understanding reality. So, what are space and time ultimately? From what we've learned, space and time are far from the simple, immutable backdrop we once assumed. They form a unified, dynamic entity, space-time, that is flexible and intertwined with the matter and energy of the universe.
Space and time can twist and warp under gravity, carrying planets in their curves and slowing clocks in their depths. They can expand, giving birth to a vast cosmos from an initial concentrated flash. They encode the causal structure of reality, what can affect what, through the finite speed of light, acting as a cosmic speed limit. They allow for the richness of cause and effect, the unfolding of cosmic history, while also humbling us with the relativity of our perspectives. And yet, even with Einstein's masterpieces, space and time retain some of their mystery. At the smallest scales, they beckon us toward a new understanding that might overthrow the continuum picture for something quantum and granular or emergent. When we push into the domain of the very tiny or the very early universe, our current theories falter, hinting that our journey to truly comprehend space-time is not finished. Future breakthroughs, perhaps a successful theory of quantum gravity, may tell us if space and time are made of bits of information or tiny loops or something we can't yet imagine. Each discovery seems to transform these concepts, from absolute to relative, to dynamical, to maybe even dispensable in favor of something deeper. Practically, space and time are the canvas of existence. They're how we make sense of where and when things happen. Without them, we can't formulate any physical law or even the notion of an event. In that sense, they are fundamental to our description of nature. Philosophically, whether they are fundamental elements of reality or emergent from something else remains an open question. Perhaps one day we'll find that even space and time are products of a more fundamental process. As we wrap up, consider how far we've come. Our ancestors looked at the regular motions of the sun and stars and the ticking of clocks and assumed time was universal and space was just emptiness. Now we know of time dilation, curved space, expanding universes, and the possibility that space and time might morph or emerge from quantum reality. Each layer of understanding adds depth to what these entities are. And through it all, we humans, living within space and time, have leveraged these discoveries. Technologies like GPS, as mentioned, rely on understanding relativity. The synchronization of global communications, satellite imaging, all these depend on treating space and time carefully. On another front, pondering the nature of time enriches fields from philosophy to neuroscience, how the brain perceives time, and even art and literature. There's practical, there's scientific, and there's existential significance in the question.
In a very real way, asking, what actually are space and time, is like asking about the framework of reality itself. We may not have a final answer, but we have a compelling story so far. Space and time are the fundamental stage and participant of the universe, woven together in a four-dimensional tapestry that is at once elegant and bizarre. They shape the cosmos and are shaped by it. They are, as best as we can tell today, the fabric of everything. As science presses onward, we will continue tugging at that fabric, peering at the threads, trying to understand the weave. Maybe someday we'll pull the veil aside and see a deeper layer of the cosmic design. Until then, every moment and every meter we explore teaches us a bit more about this strange, wonderful union of space and time, the arena in which our lives and all of history take place. It's a pursuit that not only expands our knowledge of physics, but also deepens our appreciation of just how remarkable reality is. So the next time you check the time or pace across a room, remember, you're engaging with two of the most profound phenomena in the universe. Space and time are everywhere around us, yet their true nature continues to inspire, challenge, and amaze us. And that makes our everyday experience of moving through space and time all the more extraordinary.